Hello, and welcome to the Sleepy Astronomer. I'm so glad you found your way here. Tonight, we aren't simply stargazing, we're exploring something darker, something that bends space-time itself, something where gravity becomes so strong that nothing can escape, not even light. Tonight, we're drifting through 100 gentle facts about black holes, the most extreme objects in the universe. Places where matter ends and mystery begins, where the fabric of space curves back on itself, where time slows to a stop at the edge of forever. If this exploration helps you unwind or fills you with quiet wonder as you drift towards sleep, feel free to give the video a like. And if you'd like to help others discover these peaceful cosmic journeys, a subscription truly helps this little corner of the universe grow. So, settle in, find your most comfortable position, and let your thoughts drift as we begin our gentle journey through 100 facts about where space-time curves beyond recognition, where the universe keeps its deepest secrets, and where darkness holds infinite power. A black hole is a region of space where gravity becomes so strong that nothing can escape, not even light. Think about that for a moment. Light, which travels faster than anything else in the universe, which crosses the vast emptiness between stars, which has been journeying since the beginning of time itself. Even light cannot break free. Gravity becomes absolute. The pull becomes infinite. And at that boundary, at that edge, escape is no longer possible. It's a threshold written into the fabric of reality itself. They are not cosmic vacuum cleaners, though. That's a common misunderstanding. Black holes don't roam through space sucking up everything around them. They're not hungry. They're not hunting. They don't reach out and grab. They're simply objects defined by pure curvature of space-time. Imagine space-time as a fabric and a black hole as the deepest well that fabric can form. Matter doesn't get sucked in the way water spirals down a drain. It falls because the geometry of space itself has curved so sharply that all paths lead inward. It's gravity in its most extreme expression, space-time bent beyond recognition, the universe folding in on itself. Einstein's theory of general relativity first predicted their existence in 1915. It was a revolutionary idea, that gravity isn't a force pulling objects together, but rather the curvature of space-time itself. Massive objects bend the fabric of space and time around them, and other objects follow the curves. Einstein published his field equations in November of that year, a set of mathematical relationships describing how matter and energy warp space-time. They were beautiful, elegant, and deeply strange. Even Einstein wasn't sure what all the solutions might reveal. The equations were like doors, and he didn't know what lay beyond each one. Within months, Carl Schwarzschild solved Einstein's equations while serving in World War I. Picture this scene. The year is 1916, the Eastern Front, artillery and trenches and the grinding chaos of war. And there, in the midst of it all, a German astronomer named Carl Schwarzschild receives Einstein's newly published paper on general relativity. Between military duties, in whatever quiet moments he could find, Schwarzschild worked through the mathematics. While others fought, he calculated. He found an exact solution to Einstein's field equations, the first anyone had discovered. It described what happens when all of a star's mass collapses into a single point. There was a critical radius, he calculated, beyond which nothing could escape, not even light. The mathematics was clear, elegant, undeniable. He sent a paper to Einstein, who presented it to the Prussian Academy in January 1916. Schwarzschild was still at the front, still serving, still calculating the geometry of space-time while war raged around him. And then, within months, he was gone. Schwarzschild died in May 1916 from a disease contracted during the war. He was only 42. He never knew that this solution, his final contribution to physics, would become one of the most important descriptions in all of cosmology. He never knew that his name would be attached to the radius that defines a black hole's point of no return. He died thinking he'd simply solved an interesting mathematical puzzle. He had no idea he'd described the edge of forever. The Schwarzschild radius became the name for the event horizon boundary, that critical distance, the edge beyond which return is impossible. For any mass, there's a specific radius where, if you compress that mass small enough, it becomes a black hole. For the Sun, that radius is about 3 kilometers. Compress all the Sun's mass into a sphere 3 kilometers wide, and you'd have a black hole. For Earth, the Schwarzschild radius is only 9 millimeters. Every object has one. It's just that most objects aren't compressed enough to reach it. Your body has a Schwarzschild radius too, though it's unimaginably small. It's the size your mass would need to be compressed to in order to become a black hole, a thought both amusing and unsettling. Einstein himself didn't believe black holes were real. This is one of the strange ironies of science. The man whose equations predicted them thought nature would prevent such extreme objects from forming. He believed there must be some mechanism, some law, some principle that would stop matter from collapsing beyond a certain point. The mathematics said it was possible, but Einstein's intuition said it was too strange, too extreme. Surely the universe had limits. Surely there were boundaries even gravity couldn't cross. He wrote papers arguing against their physical reality, trying to prove they were impossible despite what his own equations suggested. For decades, mainstream physics agreed they were mathematical artifacts, not physical reality. Black holes were treated as curiosities, interesting solutions to equations, but not actual objects you'd find in space. Theorists would discuss them in papers, mathematicians would explore their properties, but few astronomers seriously expected to discover one. They were filed away as one of those strange predictions that mathematics can generate. Beautiful, perhaps, but not real. The universe, most physicists assumed, was more reasonable than that. More comprehensible, less extreme in its possibilities. But the idea is older than Einstein. In 1783, more than a century before general relativity, an English clergyman and natural philosopher named John Michell imagined what he called dark stars. He reasoned that if a star were massive enough and compact enough, its gravity might be so strong that light couldn't escape. He couldn't explain it with curved spacetime. That concept didn't exist yet. But he understood enough about gravity and the speed of light to realize that, in principle, such objects might exist. Stars so dense that even light, which he knew travelled at finite speed, couldn't break free. It was a remarkable leap of imagination for the 18th century. His paper was forgotten for 2 centuries, until Einstein's theory made the concept unavoidable. Michell's work sat in archives, unread, dismissed as speculation. No one had the framework to understand what he was suggesting. The tools didn't exist yet, the language wasn't ready. But when general relativity arrived, when Schwarzschild's solution revealed the same possibility through entirely different mathematics, astronomers went back and found Michell's paper. And there it was, the same idea, the same strange prediction, dark stars, black holes, different eras, different language, same impossible truth. Sometimes an idea has to wait for the world to catch up. Sometimes the mathematics arrives first, and reality follows centuries later, patient and inevitable. Michell saw it through Newton's laws. Schwarzschild saw it through Einstein's geometry. And both were describing the same profound truth about how extreme gravity reshapes the universe. It's a reminder that some truths are so fundamental, so woven into the structure of reality that they reveal themselves again and again through whatever lens we look. In 1939, Robert Oppenheimer and Hartland Snyder modelled stellar collapse, showing massive stars could collapse beyond any possible support. They worked through the mathematics carefully, following what happens when a star runs out of fuel. Nuclear fusion stops. The outward pressure that's held the star up for millions or billions of years suddenly vanishes, and gravity, which has been waiting patiently all that time, finally wins. The star collapses inward. They showed that for massive enough stars, nothing could stop this collapse. No known force, no physical principle. The star would fall through its own Schwarzschild radius and keep falling, becoming what we now call a black hole. It was a profound paper, published in the Physical Review, just as the world was sliding into chaos. But World War II interrupted this research, and the idea lay dormant for decades. When war came, physicists had more pressing concerns than the theoretical deaths of distant stars. Oppenheimer himself would soon be pulled into the Manhattan Project. His attention turned from collapsing stars to splitting atoms. The question of what happens to massive stars was set aside, filed away, almost forgotten. Papers went unread. Theories gathered dust. For 20 years, almost no one thought seriously about black holes. The universe's most extreme objects waited quietly in the margins of forgotten journals, patient as always, while humanity focused on more immediate terrors. In the 1960s, X-ray astronomy revealed strange objects in the sky. New instruments launched above the atmosphere began detecting X-rays from space, a form of light our eyes can't see, and Earth's atmosphere normally blocks. Before this, astronomy was done mostly in visible light and radio waves, but X-rays opened a new window, revealing things that had been invisible before. And scattered across the sky, astronomers found sources of intense X-ray emission. Bright points of incredibly high-energy light, far more energetic than anything a normal star should produce. Something out there was heating matter to millions of degrees. Something was releasing enormous amounts of energy from very small regions of space. Cygnus X1 was discovered, a powerful X-ray source with no visible counterpart. In the constellation Cygnus, the Swan, astronomers found one of the brightest X-ray sources in the entire sky. They called it Cygnus X1, the first X-ray source found in that constellation. When they looked at that spot with optical telescopes trying to see what was producing all those X-rays, they saw a blue supergiant star, bright, hot, massive, unremarkable in itself. But the X-rays weren't coming from the star itself. They were coming from something nearby, something invisible, something orbiting the star, pulling matter away from it, heating that matter to extraordinary temperatures before it disappeared into darkness. Something massive was pulling matter from a visible companion star, heating it to millions of degrees before the matter disappeared. The blue supergiant wasn't alone. Careful observations revealed it was in a binary system, orbiting something unseen every 5.6 days, and that invisible companion was stealing matter from the star's outer layers. As the gas spiraled inward toward the invisible object, friction heated it until it glowed with X-rays. The matter would glow brighter and brighter, hotter and hotter, releasing enormous energy and then suddenly vanish, disappearing as if crossing some invisible boundary, as if falling past a point from which there was no return. The pattern was unmistakable to anyone who knew what to look for. The invisible object was too massive to be a neutron star. Astronomers could measure its mass by watching how it affected its companion star's motion. The two objects orbit their common center of mass, and the companion star wobbles in a predictable way. They did the calculations carefully. The invisible object contained at least several times the Sun's mass, possibly more. That ruled out most explanations. A neutron star, the collapsed core of an exploded star, can only exist up to about 3 solar masses. Beyond that mass, even neutron degeneracy pressure, the quantum mechanical force holding neutron stars up, can't hold against the collapse. Whatever was in Cygnus X1 was heavier than that limit. Significantly heavier. There was only one explanation that fit. In 1974, Stephen Hawking bet against Cygnus X1 being a black hole. This is one of science's more delightful moments, and it tells you something about how even brilliant scientists think. Hawking, who had spent years developing black hole theory, who had made fundamental contributions to understanding these objects, made a bet with fellow physicist Kip Thorne that Cygnus X1 was not a black hole. Why would he bet against his own research? It was insurance, he explained, a hedge against disappointment. If black holes turned out not to exist after all, if his life's work was built on mathematical fantasy, at least he'd win the bet. The terms were charmingly specific. If Hawking won, Thorne would give him a subscription to Private Eye, a British satirical magazine. If Thorne won, Hawking would give him a subscription to Penthouse magazine. Science can be wonderfully human sometimes. Evidence mounted throughout the 1970s, and Hawking finally conceded the bet in 1990. More observations of Cygnus X1 came in, better measurements of the companion star's orbit, refined calculations of the invisible object's mass, X-ray observations showing the telltale signature of matter, spiraling inward and vanishing at a specific radius. Each new piece of evidence pointed the same direction. The invisible object was compact, massive, and dark. It matched every prediction for a black hole. The case was becoming overwhelming, undeniable. After 16 years of accumulating evidence, Hawking admitted defeat. The story goes that he broke into Thorne's office at Caltech while Thorne was away and signed the bet concession document, adding his thumbprint for good measure. It's a moment that captures something essential about the scientific process. Not stubbornness in the face of evidence, but willingness to change your mind when the data speaks clearly enough. Even if it means conceding a bet and, more significantly, admitting that the universe is exactly as strange as your own mathematics predicted. Science had won. Black holes were real, not mathematical curiosities, not theoretical artifacts, real objects existing in real space, with real effects on the matter and light around them. The mathematics hadn't lied. Einstein's equations, solved by Schwarzschild in a trench during World War I, had predicted something true about the universe. The universe was stranger than even Einstein had been willing to accept, more extreme in its possibilities than human intuition wanted to allow. And somewhere in the constellation Cygnus, about 6,000 light-years away, matter continues to spiral into darkness. Right now, as you rest here, gas from that blue supergiant star is being pulled toward the black hole. It's heating up, glowing with X-rays, crossing that invisible boundary, falling toward a point from which nothing returns. The bet was settled decades ago. The search succeeded. But the mystery, the wonder of what actually happens at that boundary and beyond remains. For decades, they had awkward names: frozen stars, collapsed stars, dark stars, gravitationally completely collapsed objects, which is quite a mouthful and doesn't exactly roll off the tongue. Scientists struggled with the terminology, not because they couldn't agree, but because no name seemed quite right. These objects were so strange, so outside normal experience, that language itself seemed inadequate. Imagine trying to name something that shouldn't exist, something your intuition rejects even as your mathematics insists it's real. The names were technical, clunky, forgettable. They didn't capture the essence of what these things actually were. They didn't convey the strangeness, the finality, the sheer extremeness of what happens at these objects. In 1967, physicist John Wheeler coined the term black hole at a conference, frustrated with clunky terminology. It happened in December at a conference in New York. Wheeler was giving a talk about these gravitationally collapsed objects, and he kept stumbling over the words. The phrases were awkward, interrupting the flow of his thoughts, making it hard to communicate clearly. During the question period, someone in the audience suggested the term black hole, or maybe Wheeler himself said it, testing how it sounded. The story has been told different ways over the years, but however it happened, Wheeler seized on it immediately. 2 words, simple, vivid, perfect, something black, dark beyond darkness, a hole in space, though not really a hole at all, more like a pit from which nothing escapes. It was one of those rare moments where the right words arrive at exactly the right time. The name stuck immediately. It was vivid, memorable, slightly ominous. Within months, everyone was using it. Other physicists picked it up in their papers. Journalists loved it in their articles because it gave them something concrete to work with. The public understood it instantly, even if they didn't understand the physics behind it. Black hole entered the language, became part of the vocabulary, a phrase people knew even if they'd never studied astronomy. 2 words that captured something essential about these objects: the darkness, the inescapability, the sense of falling into something from which there's no return. It worked as metaphor and description simultaneously. The best names always do. Some scientists thought it too informal, even vulgar, but Wheeler understood the power of language. There were objections, naturally. Science tends to prefer precision over poetry, equations over metaphors. Some physicists thought black hole was too colloquial, too casual for a serious scientific concept. Others worried it was misleading, since these objects aren't really holes, and aren't exactly black in the way we usually think of blackness. A few even suggested the term was slightly improper, given that black hole already had certain meanings in other contexts. But Wheeler knew something important about how ideas spread. Good names help concepts travel. Clear language makes thinking easier, and a memorable term makes people curious, draws them in, invites questions. He was absolutely right. By the 1970s, black hole became universal. The term appeared everywhere: scientific papers, textbooks, popular articles, science fiction stories. It transcended its origin as conference shorthand. You could say black hole to almost anyone, anywhere in the world, and they'd have some sense of what you meant. Even if the details were fuzzy, even if the physics remained mysterious, the concept registered. A region of space where gravity becomes so extreme that escape is impossible. The name carried the idea efficiently, elegantly. It became one of the most recognized terms in all of science, right up there with Big Bang and evolution and DNA. And like those terms, it made an abstract mathematical concept feel real and graspable, something you could picture even if you couldn't fully understand it. Roger Penrose proved in 1965 that singularities were inevitable in collapsing stars. This was a profound piece of mathematical work, done just a couple years before Wheeler popularized the name. Penrose showed that once a star begins collapsing past a certain point, nothing can prevent a singularity from forming. No physical process, no quantum effects, no pressure or force could stop it. The collapse becomes inevitable. written into the mathematics of general relativity itself. It was work that would eventually earn him the 2020 Nobel Prize in Physics. 55 years after he'd done it. Sometimes the most important contributions take decades to be fully recognized. Sometimes you have to wait for the world to understand what you've proven. Stephen Hawking extended these singularity theorems, showing they applied to the Big Bang itself. Hawking took Penrose's methods and ran with them, applying the same mathematical techniques to cosmology. If collapsing matter inevitably produces singularities, then running time backward, the expanding universe must have emerged from a singularity. The Big Bang wasn't just an explosion from a very small point. It was the universe emerging from a true singularity, a place where density becomes infinite, and the laws of physics as we know them break down completely. The mathematics of black holes and the mathematics of cosmic origins turned out to be deeply connected, mirror images of each other, two sides of the same fundamental physics. These theorems established that black holes weren't just possible, they were inevitable. The universe's structure, its laws, its geometry, all pointed toward their existence. Einstein's equations didn't just allow black holes, they required them. Any sufficiently massive star that runs out of fuel will eventually collapse into one. Any universe dense enough will have emerged from one. The mathematics was clear, elegant, and unavoidable. Black holes weren't mathematical artifacts or theoretical curiosities anymore. They were fundamental features of reality, as inevitable as gravity itself, as certain as the stars burning in the night sky. And now, finally, after decades of awkward terminology and uncertain names, they had a name that did them justice, a name that would stick, a name that captured the darkness and the mystery and the finality in just two simple words that anyone could understand. The event horizon is the boundary of no return. It's a line you can cross, but only in one direction. Step across it, and you're committed. There's no changing your mind, no turning back, no escape velocity high enough to save you. It's not a physical surface you could touch or see. You wouldn't feel anything special as you crossed it. There's no barrier, no wall, no sudden resistance. Just a mathematical boundary in space-time, where the rules change absolutely. Beyond that line, all paths lead inward. Every possible future points toward the center. The event horizon is where choice ends. It's not a physical surface, but a region in space-time where escape velocity equals the speed of light. Think about escape velocity for a moment. On Earth, you need to reach about 11 kilometers per second to escape into space. Launch anything slower, and gravity pulls it back down. The Moon's escape velocity is lower because the Moon is less massive. Jupiter's is higher. Each object has its escape velocity, the speed needed to break free. At a black hole's event horizon, that escape velocity reaches 186,000 miles per second. The speed of light, the cosmic speed limit. Nothing can go faster, which means nothing can escape. Inside the event horizon, space and time literally trade places. This is one of the strangest predictions of general relativity, and one of the hardest to grasp. Outside a black hole, time flows forward, and you can move in any spatial direction. You can go left or right, forward or backward, up or down. But cross the event horizon, and something profound happens. The roles reverse. Time becomes a spatial dimension pointing inward toward the singularity. Space becomes temporal. Your future, literally your forward direction in time, is now inward. Just as you can't move backward in time outside a black hole, you can't move outward in space inside one. Every clock tick takes you closer to the center. Every moment is a step deeper. Forward in time means inward in space. The singularity isn't just in your future, it is your future. Every possible path you could take, every choice you can make, every direction you could turn, they all lead there. The future is no longer later, it's deeper in. This isn't metaphor or poetic language. This is the actual geometric structure of space-time inside an event horizon. The mathematics is clear about this, even if our intuition rebels against it. Time and space switch their character. The center becomes your destiny not because you're pulled there, but because forward in time points that way. Nothing, not even light, can travel back out once inside. Light always moves at the speed of light, obviously. That's its nature. But inside the event horizon, even travelling at maximum speed in the outward direction, light still moves inward. The geometry of space-time has curved so sharply that all outward paths curve back toward the centre. A photon trying to escape would be like someone running up an escalator that's going down faster than they can run. The photon moves at light speed, but space-time itself is falling inward faster than that. So, the light falls too, despite moving at the fastest speed possible. The size of this boundary is called the Schwarzschild radius. It's the distance from the centre where the event horizon forms. The radius depends only on mass. More mass means a larger Schwarzschild radius. The formula is simple and elegant. Take the mass, multiply by a constant, and you get the radius. It's one of those beautiful relationships where complexity collapses into clarity. Every mass has its Schwarzschild radius, the size it would need to be compressed to in order to become a black hole. For a black hole with the mass of the Sun, that radius is about 3 kilometers. Imagine compressing the entire Sun, all its mass, all 333,000 times the mass of Earth, into a sphere just 3 kilometers wide. 6 kilometers across, about the size of a small town. That's how compact you'd need to make it for the Sun to become a black hole. The actual Sun is nearly 1.4 million kilometers across. So we're talking about compressing it down to about 1/400,000th of its current size. It's hard to even picture that kind of compression. For Earth's mass compressed to a black hole, the radius would be only 9 millimeters, less than half an inch. Take our entire planet, everything, everyone, all the oceans and mountains and cities, and compress it down to the size of a marble. That's Earth's Schwarzschild radius. It's a strange thought. You could hold the mass of the entire Earth in your hand, if it were compressed enough. Of course, the tidal forces would destroy you long before you got that close, but mathematically, that's the size. 9 millimeters, the mass of a world compressed to something smaller than a grape. The more massive the black hole, the larger the event horizon. This is a linear relationship. Double the mass, double the Schwarzschild radius. Make it 10 times more massive, the radius becomes 10 times larger. The Milky Way's central black hole, Sagittarius A-star, contains about 4 million times the Sun's mass. Its Schwarzschild radius is about 12 million kilometers. That's 17 times the radius of the Sun. Large, certainly, but in the context of the galaxy, it's tiny, a point. The most massive object at the galaxy's centre, yet small enough that you'd need a telescope to see it from Earth orbit, if you could see it at all. Beyond the event horizon lies the singularity, a point where density becomes infinite and the laws of physics break down, or at least where our current understanding breaks down. We don't really know what happens at a singularity. The equations produce infinities, which usually means the equations are failing. Not that physical infinities actually exist. Maybe quantum gravity, when we figure it out, will smooth the singularity into something finite. Maybe there's a smallest possible size. and the singularity is really just extremely small rather than infinitely small. Or maybe true infinities do exist at the center of every black hole. We don't know. It's where our understanding ends and mystery begins. The singularity is hidden behind the event horizon, forever out of reach, forever unobservable. We can't look inside. We can't send probes. We can't receive signals. Everything that falls past the event horizon is lost to us, cut off from the universe we inhabit. The singularity keeps its secrets. It's a fundamental limit to knowledge built into the structure of reality. Some questions may have no answers we can ever access, and perhaps that's appropriate. Perhaps the universe is entitled to keep some mysteries to itself, hidden in the darkness at the center of every black hole. What happens if you fall in? The answer depends on the black hole's size. Not all black holes are created equal, and your experience falling into one would be dramatically different depending on whether you chose a small one or a large one. Though chose might be the wrong word. It's unlikely you'd have much choice in the matter. But if you did, if you could select which black hole to fall into, size would matter enormously. The difference between a stellar mass black hole and a supermassive one is the difference between instant death and a few final hours to contemplate your situation. For a stellar mass black hole, you'd die long before reaching the horizon from tidal forces. These are the black holes that form from collapsed stars, typically containing between 3 and a few dozen times the Sun's mass. Their event horizons are small, just a few to maybe 100 kilometers across, and the tidal forces near them are ferocious. You wouldn't make it to the event horizon. You'd be torn apart well before that point, while still technically outside the black hole. It's not a pleasant way to go, though at least it would be relatively quick. Spaghettification is the technical term. Yes, that's the real scientific terminology. Astronomers have a dark sense of humor sometimes. The word describes exactly what it sounds like. As you fall toward a stellar mass black hole, your feet get closer to the center than your head. Gravity increases with proximity, following the inverse square law. So your feet experience stronger pull than your head. This difference, this gradient in gravitational force, is called a tidal force. The same thing that creates ocean tides on Earth, but much, much stronger. You're stretched lengthwise and compressed sideways because your feet experience stronger gravity than your head. At some point, the difference exceeds what your body can withstand. Your feet are pulled harder than your head. You stretch, not metaphorically, actually physically stretch. Bones separate, tissues tear, molecules break apart. The stretching continues, intensifying as you fall closer. Eventually, atomic bonds snap. You become a stream of particles stretched into a long, thin line, like spaghetti, hence the name. This happens before you even reach the event horizon of a small black hole. The technical term for this process of tidal disruption is spaghettification, and it's exactly as unpleasant as it sounds. The gradient becomes so extreme that it tears atoms apart. Think about that for a moment. Your body is made of atoms. Those atoms are held together by electromagnetic forces, bonds between electrons and nuclei. These forces are strong. They're what give matter its structure, its solidity. But tidal forces near a stellar mass black hole become stronger than atomic bonds. The difference in gravity from one side of an atom to the other becomes enough to overcome the forces holding that atom together. You don't just get torn apart at the human scale. You get torn apart at the atomic scale, reduced to your component particles, stripped down to the most fundamental level. For a supermassive black hole, tidal forces at the horizon are gentle enough that you could cross without noticing. This is the strange mercy of larger black holes, the ones at the centers of galaxies containing millions or billions of times the Sun's mass. Their event horizons are enormous, millions or even billions of kilometers across. And because they're so large, the tidal forces at the horizon are surprisingly gentle. The difference in gravity between your head and your feet would be negligible. You could cross the event horizon without feeling anything unusual. You might not even realize you'd crossed it. You'd survive the passage through the event horizon, still taking only minutes or hours to reach the singularity. After crossing, you'd be committed. You couldn't turn back, but you'd still be intact, still conscious, still yourself. You'd have time to think, to observe, to wonder. How much time depends on the black hole's size and your trajectory? For the black hole at the center of our galaxy, you might have several hours. Time enough to contemplate your situation, though perhaps that's not actually a mercy, knowing what's coming and being powerless to stop it. But at least you'd cross the boundary intact. Looking back as you fall, the universe would appear to speed up. This is one of the strange effects of extreme gravity on time. Outside the black hole, time flows normally. But from your perspective, falling inward, time outside would appear to accelerate. Stars would zip across the sky. Galaxies would spin faster. You'd watch the cosmos's entire future unfold in fast forward. Everything that happens outside after you cross the horizon would play out before your eyes, compressed into your final moments. It's a window into eternity, though not one you'd probably enjoy. Stars zipping across the sky as you watch the cosmos's entire future in fast forward. The light from distant objects would be blue shifted as you fall toward them, compressed to higher frequencies. The universe would brighten and speed up. You'd see events that haven't happened yet, from the outside perspective. Stars being born and dying, galaxies colliding, the far future arriving all at once. Of course, this is all theoretical. No one's ever fallen into a black hole and reported back. But the mathematics predicts this is what you'd see if you could somehow survive long enough to look. Looking forward, you'd see increasing darkness as light becomes compressed and distorted. Ahead of you, toward the singularity, light would be redshifted, stretched to lower frequencies and longer wavelengths. The view would darken, the center would appear as an absence, a void, though not because there's no light, because the light itself is being stretched beyond visibility, the singularity approaching, inevitable, inescapable, not visible but present, your future made manifest as a growing darkness ahead. The singularity approaching inevitably, every moment takes you closer. Every tick of your clock is a step deeper into a region where physics breaks down. You can't stop. You can't slow down. You can't change direction. The singularity is your future now, in the most literal sense. It's where you're going, because forward in time points there. And what happens when you reach it? We don't know. Our equations fail. Our physics breaks down. Maybe you're crushed to infinite density. Maybe quantum effects intervene. Maybe something we can't imagine happens. The singularity keeps its secrets. And you, falling toward it, would be the last person to discover what lies at the center of everything. Matter falling toward a black hole forms an accretion disk. Not everything falls straight in. Most matter approaches from the side, carrying angular momentum, that property of rotating or orbiting objects that keeps them spinning. As gas and dust spiral inward toward the black hole, they form a flat rotating disk, like water circling a drain, but on a cosmic scale. This is called an accretion disk. It's one of the most energetic structures in the universe, though the black hole itself remains dark and silent at the center. All the light, all the energy, comes from the matter swirling around it. A spinning disk of gas and dust orbiting before plunging in. The disk can extend for millions of kilometers, sometimes billions, depending on how much matter is falling in and how fast the black hole is spinning. It's not a solid structure, it's more like a traffic jam of particles. Each one orbiting at whatever speed keeps it temporarily stable at that distance. Closer to the black hole, particles orbit faster. Further out, they move more slowly. The whole disk shears and grinds against itself, inner parts moving faster than outer parts. And that grinding generates heat, enormous amounts of heat. Friction in this disk heats it to millions of degrees, making it glow brightly in X-rays. The particles rub against each other, colliding, transferring energy. Friction at cosmic scales. The disk heats up until it glows, not the dull red of a hot stove or the yellow of molten metal. Hotter than that. Hot enough to emit X-rays, the kind of high-energy radiation that requires temperatures in the millions of degrees. The accretion disk around an active black hole can outshine the entire galaxy the black hole lives in. Not bad for something that's supposed to be dark. Magnetic fields can twist and eject material as powerful jets shooting out at nearly the speed of light. Black holes don't just swallow everything that comes near. Sometimes they throw things back out. Magnetic fields in the accretion disk, generated by the swirling charged particles, can become twisted and amplified. These fields can channel some of the infalling matter and redirect it outward, perpendicular to the disk. The result is jets, narrow beams of particles and energy shooting out from the black hole's poles at a significant fraction of light speed. It's one of the universe's more impressive magic tricks. A black hole from which nothing escapes, launching material across space. These jets can stretch across entire galaxies. They're not small, they're not brief. Some jets extend for hundreds of thousands of light years, punching through the galaxy, shooting out into intergalactic space. They're the longest structures in the universe, dwarfing galaxies themselves. A black hole might be just a few million kilometers across at the event horizon, but its influence extends across 500,000 light years through these jets. They carve through space, creating bubbles and cavities in the surrounding gas, affecting star formation across enormous distances. The smallest objects create the largest effects. The black hole itself emits no light. This is worth remembering. Everything we see, all the brightness, all the energy, comes from matter outside the event horizon. The black hole is dark. It's always dark. It doesn't glow. It doesn't radiate. It doesn't shine. What glows is the matter around it, the matter falling toward it, the matter being heated and compressed and accelerated before it crosses the boundary. The black hole is the absence at the center of all that light, the silent darkness that creates by its very presence some of the brightest objects in the universe. Only what surrounds it does. The accretion disk glows, the jets glow, the companion stars, if there are any, glow. But the black hole itself? Nothing. It's invisible. You can only see it by what it does to everything around it, by the hole it makes in the light, by the way matter spirals toward it and then vanishes. It's defined by absence, by what's not there rather than what is. A shadow in the shape of curved spacetime. Rotating black holes drag spacetime around with them in a region called the ergosphere. This gets even stranger. If a black hole is spinning, and most probably are, it doesn't just curve spacetime, it twists it. Imagine spacetime as fabric, and the black hole as a massive ball spinning on that fabric. The fabric doesn't just dent, it gets dragged around by the rotation. This region of drag spacetime is called the ergosphere. It exists outside the event horizon, in a space where you could theoretically still escape. But you couldn't stay still. The spacetime itself is spinning, and you'd be forced to spin with it. Inside the ergosphere, nothing can remain stationary, not even light. Everything is forced to rotate in the same direction as the black hole, caught in the cosmic current like a boat being swept along by a river. You could still escape from the ergosphere if you had enough speed and pointed in the right direction, but you couldn't just hover there. You couldn't remain at rest relative to distant stars. The space-time you're in is moving, and you move with it. It's frame dragging, one of the strangest predictions of general relativity. We've measured tiny frame dragging effects around Earth's rotation, but around a rapidly spinning black hole, the effect is extreme. Space-time itself is spinning, and anything inside must spin with it. Even light is dragged around by the black hole's rotation. Photons, massless particles of light, always moving at light speed, always taking the straightest possible path through space-time. Even they can't resist the frame dragging. Even they're forced to rotate with the black hole. Light beams curve, paths twist. The geometry of space is so warped that straight lines aren't straight anymore. The black hole doesn't just trap light by gravity. It spins it, drags it, forces it into orbits and spirals. A rotating black hole is not just a well in space-time, it's a vortex, pulling everything, even light itself, into its spin. Most black holes begin life as massive stars, at least 20 times the mass of the Sun, sometimes much more. These are the giants of the stellar world, burning bright and fast, using up their fuel at prodigious rates. They live hard and die young, as the saying goes. They're rare. Most stars are smaller, quieter, living longer lives. The Sun will burn for 10 billion years. These massive stars last just a few million years, maybe 10 million at most. But while they live, they're spectacular. Brilliant blue supergiants, lighting up entire regions of their galaxies. And their deaths are even more spectacular. They don't fade quietly. They don't shrink into white dwarfs or cool slowly into darkness. They collapse, and in collapsing, some of them become black holes. When such a star runs out of fuel, its core can no longer produce the pressure needed to resist gravity. For millions of years, maybe tens of millions for the most massive stars, fusion has been generating energy in the core. That energy creates pressure, heat pushing outward, holding the star up against its own gravity. It's a balance, a tension between two forces. Fusion pushes out, gravity pulls in. The star stays stable, neither collapsing nor exploding, just burning steadily. But fusion requires fuel. Hydrogen fuses into helium, helium into carbon and oxygen into heavier elements. Each stage produces less energy, burns faster, lasts a shorter time. Eventually, for the most massive stars, you get an iron core at the center, and iron won't fuse. Fusing iron takes energy rather than releasing it. The moment iron forms in the core, the star's fate is sealed. The fusion stops, the pressure vanishes, and gravity, which has been waiting patiently for millions of years, finally wins. The core collapses in less than a second, falling inward at nearly a quarter the speed of light. When the pressure disappears, gravity wins immediately and absolutely. The core doesn't gradually shrink. It doesn't slowly compress. It plummets. The entire stellar core may be 1.5 times the mass of the Sun, maybe more, falls inward under its own weight. The collapse is catastrophically fast. In a fraction of a second, Less time than it takes to blink, the core goes from something the size of Earth to something the size of a city, then smaller still. The matter compresses, density rising to unimaginable levels, atoms crush together, electrons are forced into protons, creating neutrons. The core becomes a ball of neutrons packed as tightly as matter can be packed, or perhaps tighter. That's 70,000 kilometers per second, 1/4 of light speed, in less than 1 second. Think about what that means. 70,000 kilometers every second. The distance from Earth to the Moon is about 380,000 kilometers. The collapsing core would cover that distance in about 5 seconds. The material is in free fall, accelerating under its own immense gravity, compressed by the weight of everything above it. It's the fastest, most violent collapse possible in normal stellar evolution. And when the core reaches nuclear density, when neutrons are pressed against neutrons with no space between them, something has to give. Either the collapse stops there, held up by neutron degeneracy pressure, or it doesn't stop at all. The outer layers explode in a supernova, leaving the collapsed core behind. The core collapses, but the outer layers, everything else that made up the star, all the hydrogen and helium and heavier elements built up over millions of years, don't fall all the way in. When the core suddenly stops collapsing or compresses past a certain point, it creates a shock wave. That shock wave travels outward through the star's outer layers at tremendous speed. It takes energy from neutrinos streaming out of the core, from the sudden compression, from the rebound if there is one, and it blows the star apart. The outer layers explode outward at thousands or tens of thousands of kilometers per second. This is a supernova, one of the most energetic single events in the universe. For a few weeks, that exploding star can outshine its entire galaxy. Meanwhile, the core, hidden at the center of the explosion, has its own fate to determine. If the core's mass exceeds about 3 solar masses, nothing can stop the collapse. It becomes a black hole, 3 solar masses. That's the approximate limit, though the exact number depends on rotation and other factors. Below that, neutron degeneracy pressure, the quantum mechanical resistance that comes from packing neutrons as close as the Pauli exclusion principle allows, can hold the core up as a neutron star. The remnant is stable, incredibly dense, but stable. Above 3 solar masses, even neutron degeneracy pressure isn't enough. The weight is too great. There's no known force that can resist the collapse. The core keeps falling inward through the neutron star phase, past any possible support, through the Schwarzschild radius. It becomes a black hole. The entire process, from the moment fusion stops to the formation of the event horizon, takes less than a second. One moment there's a star burning and shining. The next there's a black hole, dark and silent. Smaller remnants become neutron stars or white dwarfs instead. Not every stellar death produces a black hole. In fact, most don't. Most stars aren't massive enough. If the initial star is massive, but not quite massive enough, perhaps 15 or 18 solar masses to start with, the core becomes a neutron star. Incredibly dense, a ball of neutrons about 10 or 20 kilometers across, spinning rapidly, sometimes pulsing with radio waves. But not a black hole. Smaller stars, ones that started with less than about 8 times the Sun's mass, don't even make neutron stars. They become white dwarfs, Earth-sized remnants supported by electron degeneracy pressure. The universe has a hierarchy of stellar corpses, white dwarfs from small stars, neutron stars from medium-large stars, black holes from the largest stars. Each type represents a different balance point where some force finally stops the collapse, except for black holes, where nothing stops it at all. Stellar mass black holes can be just 20 kilometers wide, yet contain several times the Sun's mass. It's a strange thought. The event horizon of a stellar mass black hole might be 40 or 50 kilometers across if it's on the larger side. You could drive around it in less than an hour, if driving on the surface of a black hole were somehow possible, which it absolutely isn't. The entire object is smaller than many cities. Manhattan is about 20 kilometers long. You could fit the event horizon of a typical stellar mass black hole inside the borders of a major city, and yet it contains 3, 5, 10, maybe 20 times the mass of the Sun. All that mass compressed into a region of space smaller than the area you might cover on an afternoon drive. The density is what happens when you compress multiple suns into the volume of a small city. The numbers become almost meaningless, they're so large. But the physics is clear. Perhaps 100 million stellar black holes exist in the Milky Way alone, most completely isolated and invisible. This is an estimate based on how many massive stars we think have lived and died in our galaxy over the past 13 billion years. Most of these black holes are alone, solitary objects drifting through space. No companion stars orbiting them, no accretion disks feeding them, no jets shooting from their poles, nothing falling in to create light and energy, just solitary black holes drifting through the galaxy, completely dark, completely invisible, interacting with nothing except through their gravity. You can't see them. You can't detect them with telescopes. They're there, scattered through the galaxy like dark seeds, silent remnants of ancient stars waiting in the darkness. Most of them will never be found. They'll drift through space for billions of years, maybe trillions, unseen and unnoticed, patient monuments to stars that died long before the Sun was born. The galaxy is full of these quiet ghosts. At the opposite extreme lie supermassive black holes, millions or billions of times more massive than the Sun, not 3 or 10 or even 100 solar masses. Millions, billions. These aren't formed from single stars. They can't be. No star is that massive. No star could ever be that massive. These are different creatures entirely, occupying the centers of galaxies, anchoring everything around them. They're so massive that their gravity shapes the entire galaxy's structure, influences how stars form, affects the motion of gas clouds hundreds or thousands of light years away. And yet, for all their mass, for all their influence, we still don't fully understand how they formed or grew to such enormous sizes. Every large galaxy, including ours, appears to host one at its center. This is one of astronomy's more surprising discoveries from the past few decades. It wasn't expected. It wasn't predicted. But as observations improved, as we learned to measure galactic centers more precisely, the pattern became clear. Not some galaxies, not most galaxies. Every large galaxy we've looked at carefully enough has one. There's a supermassive black hole at the center. It's almost a rule, as reliable as any pattern in astronomy. Galaxies and supermassive black holes go together. Whether the black hole forms first and the galaxy grows around it, or the galaxy forms first and creates the black hole, or they grow together in some cosmic dance of mutual influence, we're still figuring out. But the pattern itself is clear. Big galaxy, big black hole. No exceptions found yet. At the center of the Milky Way lies Sagittarius A-star, containing about 4 million solar masses. We call it Sagittarius A-star, or SGR A-star for short, because it's located in the direction of the constellation Sagittarius. When viewed from Earth, 4 million times the mass of the Sun. It's hard to picture that kind of mass. 4 million suns, all their matter, all their mass, compressed into a region smaller than Mercury's orbit around our Sun. That's our galaxy's supermassive black hole. It's there right now, about 27,000 light-years away, in the direction you'd look if you could see through all the dust and stars, sitting at the exact center of the Milky Way. We've watched stars orbit it for decades now, tracing their paths, measuring their speeds, calculating the mass needed to make them move that way. The evidence is overwhelming. There's something massive and compact at the center, and whatever it is, it's not making any light of its own. Yet its event horizon radius is smaller than Mercury's orbit, about 12 million kilometers. For all that mass, 4 million suns worth of matter, the event horizon isn't enormous on astronomical scales. It's large, certainly. 12 million kilometers is a considerable distance. Light takes about 40 seconds to cross it, but in cosmic terms, in galactic terms, it's tiny. A point. Mercury orbits the Sun at about 58 million kilometers out. The black hole's event horizon would fit inside Mercury's orbit with room to spare. 4 million solar masses compressed into a region smaller than the innermost planet's path around a typical star. The density is actually lower than for stellar mass black holes. That's one of the strange properties of black holes. The more massive they are, the lower their average density. But it's still a black hole. Still a region where escape is impossible. Still a boundary beyond which nothing returns. M87 star, the black hole in the galaxy. Messier 87 contains 6.5 billion solar masses. This is the one we've photographed, the one that appeared in newspapers and on screens around the world in 2019. The famous orange ring around darkness. The galaxy M87 is about 55 million light-years away, an enormous elliptical galaxy in the Virgo cluster. And at its center sits a black hole containing 6.5 billion times the mass of the Sun. Think about that number. Not millions. Billions. That's over 1,000 times more massive than Sagittarius A-star, the giant at our own galaxy's center. Its event horizon is about 19 billion kilometers across. You could fit the entire solar system inside it several times over. Neptune, the outermost major planet, orbits at about 4.5 billion kilometers from the Sun. This black hole's event horizon is 4 times wider than Neptune's orbit. It's genuinely difficult to comprehend that scale. How these supermassive black holes formed remains one of astronomy's biggest mysteries. This is the question that keeps cosmologists awake at night. How do you build something containing billions of solar masses? How do you assemble that much matter into a single object? Stellar mass black holes we understand reasonably well. Massive star runs out of fuel. Core collapses, black hole forms. The process is clear. Simple enough, at least in outline. But supermassive black holes, there's no star massive enough to create them directly. No star could collapse and leave behind a billion solar mass black hole. So they must grow over time, accumulate in mass gradually. But how? Do they start as stellar mass black holes and gradually swallow gas and stars until they reach millions or billions of solar masses? That's possible in principle, but the mathematics is tricky. It takes time to swallow that much matter. And as we'll see, time might be the problem. They've been found in the very early universe, when it was only 700 million years old. This is where the mystery deepens into something genuinely puzzling. The universe is about 13.8 billion years old now. We know this from multiple independent measurements. But we've found quasars, which are supermassive black holes actively feeding and shining brilliantly in galaxies that formed when the universe was only 700 million years old. less than 5% of its current age. The universe was still young, still forming its first large structures, and some of these early black holes already contained billions of solar masses. They were already enormous, already among the largest black holes we know of. But how did they get so big so fast? Far too massive to have grown from stellar origins in the time available. Here's the problem. If you start with a stellar mass black hole, maybe 10 or 20 solar masses formed from the first generation of stars, and you start feeding it matter, there are physical limits to how fast it can grow. Feed it too fast, and the radiation pressure from the infalling matter, the energy released as material heats up and glows, pushes new matter away. There's a maximum accretion rate called the Eddington limit. It's the point where radiation pressure equals gravitational attraction, even feeding at maximum rate constantly, which probably doesn't happen in reality. Growing from stellar mass to 1 billion solar masses in 700 million years doesn't quite work. The numbers don't add up. The math doesn't close. Something is wrong with our understanding. Possible explanations include direct collapse of gas clouds, primordial seeds much larger than stellar mass, or rapid feeding in the early universe. Maybe some black holes didn't form from stars at all. Maybe, in the early universe, when gas was denser and conditions were different, entire gas clouds collapsed directly into black holes without bothering with the star phase. You'd start with something already containing thousands or tens of thousands of solar masses. That gives you a significant head start on the growth process. Or maybe there were primordial black holes, formed in the chaotic conditions of the Big Bang itself, serving as seeds around which supermassive black holes could grow. Or maybe the early universe was different somehow, denser or hotter in ways that allowed faster feeding rates than the Eddington limit normally permits. We don't know yet. Each explanation has its own problems, its own questions. The mystery remains unsolved, an active area of research. The mass of a galaxy's central black hole correlates with the velocity of stars in the galaxy's bulge, suggesting coevolution, though the mechanism is unknown. This is a strange and suggestive relationship that hints at deep connections. The faster stars move in the galaxy's central bulge, the more massive the black hole at the center. It's a tight correlation, surprisingly precise, considering how different these things seem. But why should there be a relationship at all? The black hole's gravity directly affects stars very close to it, within a few light years perhaps. But the correlation extends to the whole bulge, to stars thousands of light years away. The black hole's mass is tiny compared to the galaxy's total mass, usually less than 1%. How does it influence the entire structure? How do the galaxy and the black hole communicate across such vast distances? We can measure the correlation precisely. We just don't fully understand why it exists or what maintains it. For 2 decades, Andrea Ghez and Reinhard Genzel independently track stars orbiting Sagittarius A-star. 2 astronomers working on opposite sides of the world, measuring the same stars, pursuing the same question. Ghez at UCLA using the Keck telescopes in Hawaii. Genzel in Germany using the Very Large Telescope in Chile. Both started in the mid-1990s, pointing their instruments at the center of the galaxy, watching stars move. Not over days or weeks, over years, decades. Taking image after image, measurement after measurement, slowly building up an orbital map of the galactic center. It required patience, it required precision, and it required absolute confidence that there was something worth finding. They used some of the world's largest telescopes to watch these stars move at up to 3% the speed of light. 3% doesn't sound like much until you think about what light speed means. 3% of 300,000 kilometers per second is about 9,000 kilometers per second. That's fast enough to cross the United States in less than half a second. These stars, massive objects containing more mass than the Sun, were whipping around something at speeds that seem impossible. The fastest thing humans have ever built, the Parker Solar Probe, moves at about 200 kilometers per second at its fastest. These stars were moving 45 times faster than that. Something incredibly massive and incredibly compact was pulling them around. The star S2 completes its orbit around Sagittarius A-star in just 16 years, getting as close as 17 light-hours from the black hole. S2 became the favourite, the star everyone watched most carefully. Its orbit is particularly revealing. 16 years is quick for an orbit that size. That's faster than Jupiter orbits the Sun, and S2 is travelling a much larger distance. At its closest approach, it comes within 17 light-hours of Sagittarius A-star. A light-hour is how far light travels in 1 hour, about 1.1 billion kilometres, 17 times that. Still a considerable distance, but close enough that the black hole's gravity dominates completely. Close enough that relativistic effects become measurable. S2's orbit became a laboratory for testing Einstein's predictions in extreme gravity. This work proved that a massive, compact object only a black hole fits the evidence sits at the Milky Way's centre. The evidence accumulated year after year. The star's orbits could be calculated precisely. From those orbits, you could determine the mass of whatever they're orbiting around. 4 million solar masses, give or take. And the object had to be compact, smaller than a few light-hours across, or we'd see it. We'd detect something. There's no known object that can contain 4 million solar masses in such a small volume except a black hole. Neutron stars can't be that massive. There's no cluster of stars that dense. The only explanation that fits is a supermassive black hole. The mathematics left no other option. Ghez and Genzel shared the 2020 Nobel Prize in Physics for this decades-long observational triumph. 25 years of patient work, a quarter-century of measurements, of watching stars trace their paths around an invisible centre. It's the kind of science that requires commitment, that requires believing in the result before you have it. And in 2020, the Nobel Committee recognised that achievement. Andrea Ghez became the 4th woman ever to win the Nobel Prize in Physics. Genzel shared it with her. Both had devoted much of their careers to this question, and they'd answered it definitively. There's a black hole at the centre of our galaxy, not a hypothesis, not a theory, an observed fact, proved by watching stars dance around it for decades. In 2019, the Event Horizon Telescope collaboration released the first ever photograph of a black hole's shadow, M87 star. This was the image that went around the world, the orange-yellow ring glowing against darkness, the shadow of a black hole. It shouldn't have been possible. Black holes don't emit light. You can't photograph them directly, but you can photograph what surrounds them. You can photograph the photon ring, the light orbiting at the edge, and you can see the shadow, the silhouette the event horizon makes against that glowing ring. The image came from years of work, massive amounts of data, and algorithms designed to turn scattered radio observations into a coherent picture. The EHT is a network of 8 radio telescopes spanning from Hawaii to Chile to Antarctica, creating an Earth-sized virtual telescope. To photograph M87 star, they needed enormous resolution. The angular size of M87 star's shadow, as seen from Earth, is about 42 microarc seconds. That's roughly the size of an orange on the moon. if you were trying to see it from Earth. No single telescope could resolve that. But if you combine multiple telescopes spread across the planet using a technique called very long baseline interferometry, you can create a virtual telescope the size of Earth. 8 observatories, scattered across 4 continents, observing simultaneously, their data synchronized to billionths of a second. Together, they became the largest telescope ever created. It took 8 radio telescopes across Earth working together as one. Each telescope gathered its own data. Petabytes of data. So much that it couldn't be sent over the internet. Hard drives had to be physically flown to a central location where supercomputers combined the observations. The telescopes observed M87 in April 2017. Then came 2 years of processing, calibrating, combining, running algorithms that could take scattered radio data and reconstruct an image. Multiple teams worked independently, using different methods to make sure the result wasn't an artifact of one particular approach. And when all the teams got the same answer, when all the methods produced the same ring, they knew it was real. It took Katie Booman's algorithms to reconstruct the image from scattered data. She was a graduate student when she started developing the algorithms that would turn radio telescope data into images. The problem was immense. You don't just point a telescope and see an image. You have fragments of data from different locations at different times. You need to fill in the gaps, reconstruct what the full image would look like. Booman's algorithms were crucial to making that possible. When the image was released, she became somewhat famous, the face of the project in many ways, though she'd emphasize, as all scientists do, that it was a team effort, hundreds of people across years. But her work was central to seeing what had never been seen before. It took decades of theory predicting what we should see. Einstein's equations, solved and analyzed over and over. Simulations of how light bends around black holes. Predictions of what the photon ring should look like. What size the shadow should be. How bright it should appear. All of that theoretical work provided the template. When the image came through, researchers could compare it to predictions. And there it was. The ring was the right size. The shadow was the right shape. The brightness matched expectations. Einstein's predictions made in 1915, before anyone believed black holes were real, proved accurate down to the details. The universe works exactly as the mathematics said it should. And there it was, Einstein's prediction, photographed 104 years after he first described it. April 10th, 2019. 7 simultaneous press conferences around the world, screens showing the same image, an orange ring around darkness, the first direct visual evidence of an event horizon, the first image of a black hole's shadow. After a century of theory, after decades of searching, after years of building a planet-sized telescope, after months of processing data, there it was. Simple, elegant, unmistakable, a black hole photographed at last. Not an artist's impression, not a simulation, an actual image reconstructed from actual light that had actually orbited a black hole 55 million light-years away before travelling across the universe to reach our telescopes. The universe had shown us something we'd only imagined before, and it looked exactly like Einstein said it would. In 2022, they released the image of Sagittarius A-star, showing a glowing ring of hot matter orbiting a dark centre. The second image, this one from our own galaxy's centre. Technically more challenging because Sagittarius A-star is much smaller and its accretion disk changes quickly, flickering on timescales of minutes. M87 star is enormous and changes slowly. Sagittarius A-star required different techniques, more sophisticated processing. But when the image came through, there it was again. The same pattern, a glowing ring, a dark center, exactly as predicted, exactly as it should be. Two black holes photographed now, two shadows captured, two proofs that Einstein was right, that black holes exist, that the universe really is as strange as the mathematics always said. When two black holes orbit each other, they emit gravitational waves, ripples in space-time itself. Einstein predicted this a century ago as part of general relativity. If you accelerate mass, you create gravitational waves, disturbances in the fabric of space and time that propagate outward at light speed. For most objects, these waves are unimaginably faint. The Earth orbiting the Sun creates gravitational waves, technically, but they're so weak they'd be impossible to detect with any conceivable instrument. Black holes, though, are different. When two black holes orbit each other, particularly when they're close and moving fast, the gravitational waves they produce become strong enough to measure, at least in principle, at least if you build the right instrument and you're extraordinarily patient. These waves carry energy away, causing the black holes to spiral closer together. Gravitational waves aren't just ripples passing through space. They carry energy, real energy extracted from the orbital motion of the black holes. As the waves radiate outward, spreading across the universe, the black holes lose orbital energy. As they lose energy, they spiral inward. Slowly at first when they're far apart and orbiting leisurely, then faster as they get closer. The closer they get, the faster they orbit. The faster they orbit, the stronger the gravitational waves. The stronger the waves, the more energy they carry away. It's a feedback loop. The spiral accelerates, tightening with each orbit, each pass bringing them closer. Eventually, inevitably, the black holes merge. Eventually, they merge in a violent collision, releasing more energy in a fraction of a second than all the stars in the visible universe combined. This is the moment everything has been building toward. The two black holes, perhaps orbiting each other for millions of years, slowly spiraling inward through empty space, finally come together. In the last fraction of a second before merger, they're orbiting each other hundreds of times per second, moving at a significant fraction of light speed. Then they collide, they merge, their event horizons touch and combine, creating a larger horizon around both. The space-time around them ripples violently, shakes, distorts, and then settles into a new configuration. And in that brief moment, the merger releases more energy than you can easily comprehend. More than all the stars you can see with any telescope, all the galaxies in the observable universe, all the light from billions upon billions of suns, all added together and multiplied again. On September 14th, 2015, LIGO detected the first gravitational wave signal, the Laser Interferometer Gravitational Wave Observatory. Two detectors, one in Louisiana, one in Washington State, separated by thousands of kilometers. Each one is an L-shaped tunnel system, each arm 4 kilometers long, with laser beams bouncing back and forth measuring the distance between mirrors with absurd precision. They're designed to detect incredibly tiny stretches and compressions in space-time itself, changes smaller than an atomic nucleus. And on that morning in September, at 5:51 a.m. Eastern Time, both detectors picked up the same signal within milliseconds of each other. A chirp, a rising frequency and amplitude lasting just 1/5 of a second. The signal that changed astronomy forever, though at that moment only a few people knew what had just happened. The signal came from two black holes, 36 and 29 solar masses, merging 1.3 billion light-years away. That's what the signal told them once they analysed it. once they'd confirmed it was real and not some instrumental glitch or terrestrial noise. Two black holes, each several times more massive than the Sun, spiraling together and merging somewhere in the distant universe. And it happened 1.3 billion years ago, when the universe was younger, when Earth was still in the midst of developing complex multicellular life. The gravitational waves travelled across the universe for all that time, 1.3 billion years, crossing unimaginable distances, passing through galaxies and vast voids of empty space, until finally, on September 14th, 2015, they passed through Earth. They stretched and compressed the space between LIGO's mirrors by less than 1/10,000th the width of a proton, and somehow, impossibly, LIGO detected it. In the merger, 3 solar masses were converted entirely into gravitational wave energy, according to E equals mc squared. Think about what this means. 3 times the mass of the Sun, not 3 suns worth of material burned as fuel over billions of years. 3 entire solar masses worth of matter energy, completely converted into gravitational waves in a fraction of a second. E equals mc squared. Energy equals mass times the speed of light squared. 3 solar masses multiplied by the speed of light squared. That's roughly 5 times 10 to the 47th joules, released in less than a second. For comparison, the Sun's total luminosity, all the light and energy it puts out in all directions constantly, is about 4 times 10 to the 26th watts. The merger briefly outshone in gravitational waves all the electromagnetic radiation from all the stars in an observable universe combined. The most violent event possible aside from the Big Bang itself, and we heard it. From 1.3 billion light-years away we heard it. The signal lasted 0.2 seconds, rising in frequency and amplitude like a chirp as the black holes spiraled together. 0.2 of a second. Blink and you'd miss it if you could somehow perceive gravitational waves directly, which you can't. The signal started at about 35 Hz, the low end of what humans can hear if it were sound instead of space-time ripples. It swept upward in frequency as the black holes orbited faster and faster, tightening their spiral. Higher and higher pitch, louder and louder amplitude, approaching the moment of merger, until at about 250 Hz, the moment the black holes finally touched, the signal peaked and then abruptly cut off. Silence, or rather, the new single black hole, 62 solar masses, now quietly settling into its final form, no longer producing strong gravitational waves. The chirp has become iconic in gravitational wave astronomy. Scientists have converted the signal to sound waves so people can hear what a black hole merger sounds like. A rising whoop that ends suddenly, the sound of space-time ringing like a bell. This detection confirmed Einstein's final unproven prediction and opened a new era of gravitational wave astronomy. Einstein published the theory of general relativity in 1915, introducing the idea that gravity is curved space-time. He predicted gravitational waves in 1916, showing that accelerating masses should create ripples in that curved space-time, and for 99 years, those waves remained undetected. A theoretical prediction without observational confirmation, too faint, too difficult to measure. Physicists built increasingly sensitive instruments over decades, pushing the limits of precision measurement, but gravitational waves eluded direct detection until September 2015. In one brief observation lasting less than a second, LIGO confirmed what Einstein had predicted a century earlier. Gravitational waves exist. They propagate at light speed. They stretch and compress space itself. And they carry information about the most violent events in the universe. Since then, LIGO and other detectors have observed dozens more mergers, black holes colliding, neutron stars spiraling together. We can now hear the universe in a way we never could before. We can listen to gravity itself. Since that first detection, gravitational wave astronomy has become a new window on the cosmos. We've detected dozens of black hole mergers now, each one unique, each one teaching us something new about how black holes form, how they evolve, what masses they come in, how often they merge. We've heard neutron stars collide, an event that also produces light, allowing us to observe the same cosmic collision with both traditional telescopes and gravitational wave detectors simultaneously. We've measured how fast the universe is expanding using gravitational waves as cosmic rulers, independent of other methods. We've tested Einstein's predictions in the most extreme gravitational fields possible and found them accurate every time. And we've only just begun. The detectors keep getting more sensitive, able to hear fainter signals from farther away. The catalogue keeps growing. Every new detection is another glimpse into phenomena we couldn't have imagined observing before 2015. We've added a new sense, a way of experiencing the cosmos that complements what we can see with light. We can hear what happens when the universe's most massive objects collide. We can listen to space-time itself rippling and ringing across billions of light years. In 1974, Stephen Hawking proposed that black holes emit faint radiation due to quantum effects near the event horizon. This was unexpected, revolutionary even. Black holes, by definition, don't let anything out. That's what makes them black holes. That's the whole point. But Hawking showed that if you account for quantum mechanics near the event horizon, something strange happens. Virtual particle pairs, which normally pop into and out of existence throughout space constantly, can be separated by the event horizon. One particle falls in, crossing the boundary. The other escapes, becoming real. From the outside, it looks like the black hole is emitting radiation, faint thermal radiation. The black hole glows very dimly, in a way that has nothing to do with matter falling in. It's a purely quantum effect, happening at the boundary between something and nothing. This Hawking radiation means black holes can slowly lose mass over time and eventually evaporate. If a black hole emits radiation, it's losing energy. And energy and mass are equivalent. E equals mc squared, so losing energy means losing mass. Very slowly. Incredibly slowly for any black hole you're likely to encounter. But over vast stretches of time, unimaginable eons, a black hole can radiate away all its mass and disappear entirely, evaporate into nothing, vanishing from the universe as if it had never existed, which is a strange thought. The most permanent seeming objects in the universe, the final end state of massive stars, the things from which nothing escapes, the ultimate prisons of space-time, eventually vanish. Given enough time, enough patience, even black holes die. Small black holes would evaporate faster. The smaller the hole, the hotter it is. This is one of those counterintuitive results that quantum mechanics gives us, one of those predictions that defies intuition. You might think a larger black hole would be hotter, more energetic, radiating more. But it's the opposite. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Double the mass, half the temperature. Tiny black holes are scorching hot, radiating furiously, evaporating quickly. Large black holes are incredibly cold, barely radiating at all. A black hole with the mass of a mountain would be hotter than the surface of the sun, glowing intensely. A stellar mass black hole is colder than the cosmic microwave background, the leftover radiation from the Big Bang that fills all of space at about 3 degrees above absolute zero. Stellar black holes are incredibly cold, tiny fractions above absolute zero, and would take 10 to the 67th years to evaporate. Let's put that number in perspective. That's a 1 followed by 67 zeros. Years, not seconds or minutes. Years. For context, the universe is currently about 13.8 billion years old, which is roughly 10 to the 10th years. To reach 10 to the 67th years, you'd need the current age of the universe, multiplied by itself, then multiplied by itself again and again, many times over. By then, all the stars will have burned out billions of years ago. Galaxies will have evaporated, their stars flung into intergalactic space. Protons themselves might have decayed, though we're not certain. The universe will be cold, dark, and almost completely empty. And still the stellar mass black holes will barely have begun to evaporate. They're as close to eternal as anything physical can be, but not quite eternal. Eventually, given enough time, even they vanish into radiation. But this creates a profound paradox. Quantum mechanics says information cannot be destroyed. This is one of the fundamental principles of quantum theory built into the mathematical structure of the theory itself. If you know the exact quantum state of a system now, you can in principle calculate what it was in the past and what it will be in the future. Information is preserved. It might be scrambled, mixed up, made practically impossible to recover in any realistic sense. But fundamentally, it's still there somewhere. Burn a book, and the information isn't destroyed. It's contained in the smoke, the ash, the heat radiation, the exact position and momentum of every particle produced in the fire. Difficult to recover, certainly, impossible in practice, but not destroyed in principle. Yet relativity says nothing escapes a black hole once inside. Anything that crosses the event horizon is gone, separated from the external universe by an absolute boundary, cut off. No information about what fell in can get back out. No signal, no measurement, no observation can reach from inside to outside. The black hole's exterior is characterized completely by just 3 numbers: mass, charge, and spin. Everything else about what fell in, all the details, all the information about the structure and composition and history of the matter, is hidden behind the event horizon. This is sometimes called the no-hair theorem. Black holes have no hair, meaning no additional distinguishing features beyond those 3 numbers. 2 black holes with the same mass, charge, and spin are completely identical, regardless of whether they form from stars or gas clouds, whether they've swallowed planets or photons. Hawking radiation appears completely thermal, random, containing no information about what fell in. When Hawking calculated the radiation that quantum effects should produce, he found it was perfectly thermal. It had the spectrum of heat radiation from a hot object, like a glowing piece of metal or a warm radiator, perfectly random. And thermal radiation, by its very nature, contains no information about what created it. A piece of iron glowing at a certain temperature looks exactly the same, whether it was heated by fire, electricity, friction, or anything else. The radiation doesn't encode the details of the heating process. So when a black hole evaporates via Hawking radiation, where does the information about everything that fell in go? The encyclopedia you threw in, the star that collapsed to form the black hole, every atom and photon that crossed the horizon. Where's the information? It seems to be lost, vanished, destroyed. So where does the information go? This information paradox has been unsolved for 50 years. This is the question that's haunted theoretical physicists since Hawking's discovery in 1974. Half a century of the brightest minds in physics working on this problem. If black holes destroy information, quantum mechanics is fundamentally wrong, and we need to rebuild one of the pillars of modern physics. But quantum mechanics is extraordinarily well tested. It underlies all of chemistry, most of modern technology, our understanding of matter itself. If information somehow escapes in the Hawking radiation, but the radiation is thermal and random, how is that possible? How can random radiation encode specific information? If information stays inside as the black hole evaporates, what happens to it when the black hole disappears completely? Does it wink out of existence, taking the information with it? That would violate quantum mechanics. Does something prevent the black hole from fully evaporating, leaving a remnant? What could stop it, and how would that work? It represents a fundamental conflict between quantum mechanics and general relativity, the two pillars of modern physics. This is why the paradox matters so deeply. Quantum mechanics and general relativity are the two great theories of 20th century physics, the two frameworks that describe everything we know about the physical world. Quantum mechanics governs the very small atoms and particles and forces. General relativity governs the very large planets and stars and space-time and gravity. Both theories are exquisitely accurate in their respective domains. They've been tested countless times and never found wanting, but they don't fit together easily. They're based on different principles, use different mathematics, make different assumptions about the nature of reality. And at black holes, particularly evaporating black holes, both theories are needed simultaneously. Quantum effects at the horizon, relativistic gravity everywhere else. The information paradox exposes this conflict directly. It shows us that our understanding is incomplete, that something fundamental is missing. Either quantum mechanics needs modification, or general relativity does, or our understanding of what happens at the event horizon is wrong. 50 years on, despite enormous effort, we still don't know which. The paradox remains, pointing toward new physics we haven't yet discovered. Maybe the information does escape, encoded in subtle correlations in the Hawking radiation that we haven't figured out how to calculate yet. Maybe it's stored on the event horizon itself, holographically encoded on the two-dimensional surface in a way that gets released as the black hole shrinks. Maybe black holes don't evaporate completely, leaving behind tiny remnants that contain all the information compressed into a final, tiny mass. Maybe there are modifications to quantum mechanics we haven't discovered yet. Maybe general relativity breaks down near the singularity in ways that preserve information. Or maybe our whole framework for thinking about this is wrong, and we need entirely new concepts to understand what happens. The paradox remains unsolved, a puzzle waiting for the next generation of physicists. It's a signpost pointing toward new physics, a crack in the foundation that suggests deeper truths waiting to be uncovered. Black holes, it turns out, aren't just about gravity. They're about the nature of information, the structure of reality, the limits of our current understanding. They're where physics breaks down and mystery begins. We may never see inside a black hole's event horizon. The laws of physics prevent any information from escaping. This is a fundamental limit, not a technological one. No matter how advanced our instruments become, no matter what clever methods we devise, no matter how many centuries pass, we can't look inside. The event horizon is an absolute boundary in space-time. Light can't escape to bring us information. Particles can't escape to tell us what they saw. Gravitational waves can't carry signals from inside to outside. It's not that we haven't figured out how to observe the interior yet. It's that the interior is, by definition, by the very structure of space-time cut off from observation. Some regions of space-time are simply beyond our reach, hidden not by distance or difficulty, but by the fundamental architecture of reality itself. The singularity at the center, where density becomes infinite, is where our mathematical theories break down completely. Our equations produce infinities, which in mathematics usually means the equations themselves are failing, rather than that physical infinities actually exist in nature. General relativity predicts a singularity, a point of infinite curvature, infinite density, infinite tidal forces, a place where the laws of physics as we understand them cease to make sense, where our mathematical descriptions become meaningless. But most physicists suspect this is a sign that general relativity isn't the final theory of gravity. It's a classical theory, meaning it doesn't incorporate quantum mechanics. And at the extreme scales of a singularity, scales smaller than atoms, smaller than nuclei, quantum effects should dominate. We need a theory of quantum gravity to understand what really happens at the center. But we don't have that theory yet. We're still working on it, still trying to merge quantum mechanics and general relativity into a single consistent framework. Some physicists think black holes might be connected to other universes through wormholes, though this remains purely theoretical. The mathematics of general relativity allows for wormholes, tunnels through space-time connecting distant regions or even different universes entirely, and some mathematical solutions show wormholes inside black holes, connecting the singularity to other places or times. But these are mathematical possibilities, not observed realities, not even predictions we're confident about. The wormholes in these solutions are typically unstable, collapsing before anything could pass through them, or they require exotic matter with negative energy density, which we've never found and might not exist. Or they connect to regions that can't communicate with our universe anyway, making them unobservable by definition. It's a beautiful idea, evocative and strange, the stuff of science fiction. But there's no evidence it's true. Black holes might be doorways to other universes, or they might just be extremely dense regions of our own space-time with nothing else inside. We don't know. Others propose the singularity doesn't truly exist, and quantum gravity will smooth it out into something finite. This is the more common view among physicists working on quantum gravity theories. In string theory, for instance, the singularity is replaced by something like a string, or a fuzzy ball of quantum information extended in extra dimensions. In loop quantum gravity, space-time itself has a discrete granular structure at the smallest scales, preventing true infinities from forming. The idea is that when you account for quantum effects properly, when you include the quantum nature of space-time itself, the collapse stops at some extremely small but finite size, perhaps something the size of the Planck length, about 10 to the minus 35 meters, the scale where quantum gravitational effects become important, still unimaginably small, still effectively a point from any practical perspective, but not infinite, not a true mathematical singularity, a quantum object we don't yet fully understand, but something finite, something physical, something that obeys quantum laws. Black holes represent a fundamental limit to knowledge. Some questions may have no answers we can ever access. This is perhaps the most profound aspect of black holes, the deepest lesson they teach us. They show us that the universe contains regions we fundamentally cannot observe, not because we lack the technology, or the funding, or the time, but because the physics itself prevents it. The interior of a black hole is causally disconnected from the outside universe. No signal of any kind can pass from inside to outside. This means there are truths about the universe we can never verify through direct observation, questions we can never answer by looking. What happens at the singularity? What's the internal structure of a black hole? What does it look like from inside? We can theorize, calculate, construct models, debate possibilities, but we may never know for certain. The universe keeps some secrets, and it keeps them absolutely. Yet through their shadows we glimpse the limits of knowledge itself. The event horizon is a boundary between the knowable and unknowable, a line drawn across space-time separating what we can observe from what we cannot. We can't see past it, but we can see it. The shadow, the silhouette it makes against glowing matter orbiting around, the way light bends and curves in the extreme gravity near the edge, the effect its immense gravity has on nearby objects, on stars and gas and other matter. We can study the boundary even if we can't cross it, and studying that boundary tells us something profound about the nature of knowledge itself, about what can and cannot be known, about where observation ends and extrapolation begins. Black holes make epistemology, the study of knowledge, into something physical. They turn philosophical questions about the limits of knowledge into concrete features of space-time geometry. They teach us humility in the face of infinity, showing us that mystery is built into the structure of reality. For all our scientific progress over the past few centuries, for all our sophisticated instruments and elegant theories, for all the questions we've answered and problems we've solved, we're still confronted with fundamental unknowns. Black holes remind us that the universe doesn't owe us answers. Some things remain hidden, not because we haven't looked hard enough or thought deeply enough, but because the looking is fundamentally impossible. And maybe that's appropriate. Maybe mystery is a feature of the universe, not a bug. Maybe having questions we can't answer makes the cosmos more interesting, more worthy of wonder than having all the answers would. Black holes are humbling. They show us the limits of what we can know, the boundaries of what's knowable in principle, and in doing so, they make the cosmos feel larger, stranger, more full of wonder than a completely explicable universe ever could. In the stillness at the center of everything, where space-time curves back on itself, the universe keeps its deepest secrets. This is where we end our journey through 100 facts about black holes. At the center, at the singularity, at the point where physics breaks down and mathematics produces infinities, and our understanding reaches its limit. We've come from Einstein's reluctant prediction in 1915, through decades of searching and doubt, to photographs of shadows and the sound of space-time itself, ringing with mergers. We've explored the anatomy of these objects, their birth from dying stars, their growth to supermassive scales, their ultimate mysteries. We've learned what we know, and we've learned what we might never know. The singularity remains hidden behind the event horizon. The information paradox remains unsolved after 50 years. The interior, forever beyond our reach, causally disconnected from everything we can observe, but that's fitting. Black holes are where the universe ends, where space-time curves until it closes back on itself, where gravity becomes so extreme that our best theories falter, where questions outnumber answers. And perhaps that's exactly as it should be. We've achieved extraordinary things in understanding black holes. We've measured the unmeasurable, weighed invisible objects by watching stars orbit them. We've photographed the unphotographable, capturing the shadow of a black hole's event horizon. We've heard the unhearable, detecting gravitational waves from mergers billions of light years away. We've tested Einstein's centriole predictions in the most extreme environments the universe can create and found them accurate to extraordinary precision. These are triumphs of human curiosity, ingenuity, persistence, and collaboration across decades and continents. But for all that we've learned, mysteries remain. The center stays hidden. The information paradox unsolved. The quantum structure unknown. Some questions wait not for better instruments, but for better theories, for conceptual breakthroughs we haven't had yet. We've mapped the boundary between the known and unknowable. We've photographed the edge of forever. We've listened to space-time itself, ringing like a bell with the collisions of invisible giants. And in doing so, we've discovered both how much we understand and how much we don't, how far we've come and how far we have to go. Black holes are testaments to both human knowledge and human limitations. They show us the power of mathematics to predict reality and the limits of observation to confirm predictions. They're simultaneously our greatest triumph and our greatest mystery. Objects we've proven exist, captured in images, detected through their effects on everything around them, but objects whose interiors remain forever hidden, whose deepest nature might always elude us, whose secrets might be forever locked away behind event horizons. In the darkness at the center of every black hole, nature keeps its secrets, and in that unknowability, in that permanent mystery, there's strange and terrible and wonderful beauty. And now the stars begin to dim behind your thoughts. We've drifted through 100 gentle facts about black holes, from the impossible to the inevitable, from Einstein's reluctant equations to photographs of shadows cast across the universe, from mathematical curiosities to observed realities, from darkness that taught us to see. We started with Einstein in 1915, publishing equations he didn't fully trust. We met Schwarzschild, solving those equations in a trench during World War I, never knowing his solution would define the edge of forever. We watched decades pass as the idea was dismissed, filed away, almost forgotten. Then the search began, X-ray telescopes finding strange sources in the sky. Cygnus X1 stealing matter from a companion star, Hawking making a bet against his own research, insurance against disappointment, and slowly, steadily the evidence mounted until denial became impossible. We've learned what black holes are, not vacuum cleaners roaming through space, but regions where space-time curves so sharply that escape becomes impossible, where gravity writes its most extreme statement, the event horizon, a boundary you can cross but never return from. Inside, space and time trade places. Your future becomes inward. The singularity waits at the center, hidden behind the horizon, where our physics breaks down and mystery begins. Stellar mass black holes from dying stars, supermassive giants anchoring galaxies, perhaps 100 million scattered through the Milky Way, most invisible, most alone, drifting silent through space. We've watched scientists spend decades proving they exist. Gez and Gensel tracking stars orbiting Sagittarius A-star for 20 years, measuring speeds, calculating masses, demonstrating that something massive and compact sits at our galaxy's center. The Event Horizon Telescope, 8 observatories across Earth working as one, creating a planet-sized instrument to photograph what cannot be photographed. M87 star in 2019, Sagittarius A-star in 2022. Orange rings around darkness, shadows cast by curved space-time. Einstein's predictions confirmed 104 years later, accurate down to the details. We've heard them collide. September 14th, 2015. LIGO, detecting gravitational waves for the first time. The chirp of two black holes spiraling together 1.3 billion light-years away. 3 solar masses converted entirely to gravitational wave energy in a fraction of a second. More power than all the stars in the visible universe. And we heard it. A new sense added to astronomy. A way to experience the cosmos through ripples in space-time itself. We've explored the paradoxes they create. Hawking radiation means black holes aren't completely black. They glow faintly, evaporating over timescales that dwarf the current age of the universe. But this creates a profound puzzle. If black holes evaporate, where does the information go? 50 years later, we still don't know. The information paradox remains unsolved, a crack between quantum mechanics and general relativity, pointing toward physics we haven't discovered yet. And we've learned about limits. Some things we cannot know. The interior of a black hole is forever hidden from observation. The singularity keeps its secrets. We can photograph the shadow, measure the mass, detect the waves. But we cannot look inside, cannot see what happens at the center, cannot observe where physics breaks down. Black holes teach us that mystery is built into the structure of reality, that some questions may have no answers we can access, that the universe is under no obligation to reveal everything. Look up tonight, if you can, and know that black holes are out there, scattered through the galaxy, anchoring the center of the Milky Way, merging in distant space, sending ripples across the universe. Most are invisible, silent, alone, but they're there, shaping the cosmos, bending light, warping time, the most extreme objects nature allows, the darkest things that exist yet captured now in images, detected through their effects, understood through their mathematics. We live in a universe with black holes, a universe where stars can collapse into regions of infinite curvature, where space-time can bend back on itself, where the gentlest force, gravity, builds up over distance and time until it creates the ultimate extreme, where darkness holds infinite power and mystery guards the deepest secrets, and somehow we figured this out. We predicted them with mathematics, searched for them with telescopes, found them hiding in plain sight, photographed their shadows, heard them collide, tested them against theory and found reality more strange than we imagined. 100 facts, each one a window into something profound. Black holes are where the universe ends and mystery begins, where knowledge meets its limits, where space-time curves until it closes, where Einstein's equations prove accurate and also insufficient, where we understand more than we ever thought possible and less than we wish we could, in the stillness at the center, in the darkness that cannot be penetrated, in the silence where no signal escapes, the universe keeps its deepest secrets. And that's beautiful, that's fitting, that's exactly as it should be. We've learned so much, achieved so much, measured the immeasurable, photographed the unphotographable, heard the unhearable. We've proven that the strange mathematics from 1915 describes reality. We've watched stars orbit the invisible for decades. We've listened to space-time ring like a bell. These are triumphs. But mystery remains. And maybe mystery is the point. Maybe not knowing is what keeps us curious, keeps us searching, keeps us looking up at the darkness, wondering what else is out there waiting to be discovered. This is the Sleepy Astronomer, wishing you sweet dreams under stars that may one day collapse into the very darkness we've been exploring tonight. Rest well knowing that black holes hold everything together, bend light across the universe, and keep secrets we may never uncover. The cosmos is stranger than you imagined, more mysterious than it appears, and more beautiful than words can capture. And somewhere out there in the night, In the space between stars, black holes drift on, patient, silent, inevitable, waiting in the darkness. Good night,